A tuning fork with a vibrating frequency of 180 Hz is mounted to a metal bar. One end of a uniform string is attached to the fork, the other end passes over a pulley and is attached to that mass M. And the value of M creates a standing wave pattern with these 4 loops in it, and the length of the string from one side to the other is 1.20 meters. So in part A, we want to determine the wavelength of the standing wave. This is a very simple question. You get it straight from the diagram, because what you have to remember that we discussed in class is that whenever you have one of these standing wave diagrams, the wavelength is equal to the length of exactly 2 loops. So if this whole thing, 1.2 meters, is 4 loops, that's really easy to figure out what is the length of 2 loops. In part B, we want to calculate the speed of the waves along the string. Now remember, the only way that can actually tell you the speed of waves on a string is it depends on what the string is made out of, the linear density, and also it depends on the tension in the string. But there is another equation that relates the speed with wavelength and frequency, which is this equation. Since we know the wavelength from part A, and we know the frequency at which the tuning fork is vibrating, which is the F, we could just multiply those two together to get the V, the speed of the waves. In part C, the person wishes to double the number of loops in the standing wave pattern. So we're going to go from 4 loops to 8 loops. So if you just kind of picture what that looks like. Let's see, hope something like this. 1, 2, 3, 4, 5, 6, 7. Okay, I did a little bit too many, but either way, you can see that a wavelength now, which is the length of 2 loops, is much shorter than it was before. So since we know that the speed of a wave depends directly on the tension in the string, and it depends inversely on the linear density, which we usually just call mu. Remember, mu is mass over length. Again, you don't have to know the exact equation for this, even though I'm just going to go ahead and give it to you. It's the square root of tension over the linear density. You've seen this, we've mentioned this before, you're going to see it on future assignments, but it's not required knowledge for the AP exam. They will give it to you if you need to know it. That's why it's not on the formula sheet. So what we can see here is that the speed of the wave will increase if the tension increases, and it will decrease if the tension decreases, since tension is in the numerator. So remember, we also said how speed relates to this equation right here. So if we're doubling the number of loops, we're still connected to the same tuning fork, so the F is going to be the same, but since we're doubling the number of loops, the wavelength is going to be smaller. So same F, smaller wavelength, will lead to a smaller V. So because we have a smaller V, that means we're going to have a smaller tension, which means you don't want to have as much mass hanging from the pulley, because the more mass is hanging right here, since that's connected over that pulley, the more mass leads to more tension. So you want to have less mass to lead to less tension, and that will result in a lower speed, and the lower speed results in the lower wavelength. Now it says the wave speed is directly proportional to the square root of the tension. That's shown right here. So we're just going to use proportional reasoning for this, and we want to get the new wave pattern. Since there's twice as many loops, the wavelength is going to be half as much. So if the wavelength is half as much, that means, according to this equation, the speed is going to be half as much. So now if we go down to this equation, with a speed being 1/2 as much, which I'll put right there, how does that tension have to change? Well, since tension is under the square root, that would actually be 1/4 as much, because when you take the square root of 1/4, you get 1/2. So the square root of 1/4, 1/4 of the tension, means that the mass would have to be 1/4 as much also. This hanging mass right here would have to be m over 4. In part D, if a point on the string at an antinode moves a vertical distance of 4 centimeters during one complete cycle, what's the amplitude of the wave? So let's say, if we look back at this diagram, let's take this point right here. That's a point on an antinode, and in one cycle, it's going to move 4 centimeters, which is from here down all the way to the bottom, and then back up to the top. So the amplitude is just the distance from the maximum displacement up here to where that center point is right there. So if 4 centimeters is going from here to the center, to the bottom, back to the center, and back to the top, then the amplitude would just be 1/4 of that value. So the amplitude is 1 centimeter, not the 2 centimeters. We've seen a question like this before, but it was kind of done the other way. You were told the amplitude of a wave, and you had to figure out how far the point actually moved. Now you're told how far the point moves, and you have to work backwards to figure out the amplitude. And then finally, for part E, determine what frequency tuning fork should be used in place of the 180 hertz tuning fork in order to vibrate the string in its third harmonic. But right now, because there's 4 loops, it is vibrating in its fourth harmonic, because the harmonic matches the number of antinodes, which is the number of loops. So we can figure out first what the fundamental frequency is, because the fourth harmonic would just be equal to 4 times that fundamental frequency. So the fundamental frequency is going to be the fourth harmonic divided by 4. 180, which is the fourth harmonic, divided by 4 gives you 45 hertz for the fundamental. And then to get F3, the third harmonic, we just take 3 times that fundamental to get the answer.